Okay. So as I told you, in this particular class, we will be discussing about a very, very important derivation, which is known as SFEE. What does SFEE stands for? Steady flow energy equations. Okay. So before we go into the derivation is very simple. It contains only few steps, around 3 to 4. That's it. But it's very important when it comes to your examination point of view, even for your application point of view also. The SFE has lot and lot of applications. So when you want to design a flow system, when you want to analyze, if you know certain input parameters, suppose if in case, if I take an example of a compressor like this, if I take a example of a compressor, I know few of the parameters at inlet and few of the parameters at outlet. So the parameters which are unknown can be found out. Suppose I know pressure, volume, temperature, enthalpy, entropy, everything at the inlet. Okay, and I know only volume, temperature, enthalpy, and the entropy, but I don't know what is pressure. Okay, if such in case, I can use my SFEE equation to find out what is that particular pressure. Not only that, you can even find what is the heat flow into the system, what is the workflow from the system. So every parameters can be calculated using the SFEE. So it has such an importance. That's why this particular question is being asked many, many times in your examinations also. Okay. And even in the industry, because I come from an industrial background, we use SFP a lot. Okay, when it comes to a flow measuring devices, when it comes to a heat interactions, um, all sort of work absorbing or it might be work emitting devices, we use SFE a lot. So application of this particular thing has a greater significance in an industry. Okay, so just we will go through some of the assumptions before we move into the derivations. Okay. Just kindly concentrate. So, fluid flow from one or more places. Actually, in an engineering application system, it might be any system, a thermodynamic system, or it might be a rotatory system, a mechanical system. There will be two or more the ways the fluid gets in the system, or two or more ways the fluid gets out of the system. So you cannot say the fluid enters through only one channel and gets out from a single channel. So it will be having a multiple ways of inlet and multiple ways of outlet. So in order to understand and analyze such systems, this particular application is very, very important. Okay. Next step, flow may be continuous, intermittent, steady or unsteady. That's why I use control volume concept here. Suppose, say, there is a pipe here like this going on. Okay. In this particular pipe, the water is being flowing. So sometimes the flow of the water is continuous, as in case of lick. Okay, it contains the whole of the thing. Sometimes it gets intermittent, only a partial flow would occur inside the pipe. And sometimes the flow would be steady. That means it will not change with respect to time. But sometimes the flow will be unsteady. That means the pressure and the velocity changes with respect to time. So if such is a scenario, it becomes very tedious and difficult for us to analyze the whole system. That's why the concept of control volume is being used here. So in the control volume, what we will be doing is we'll be selecting a particular part of the system, naming it as the control volume. Okay. In that particular control volume, we'll be studying the various parameters which are required for us. So that is the concept of control volume. So why is the concept of control volume is being used is because the flow will be not continuous, it will be intermittent, flow will be not steady, it would be unsteady. So and it changes all over the length of the system. So it becomes tedious and complex to analyze such systems. So generally what we'll be doing, we'll be selecting a portion of a system and where we want to study the things and we will name it as the control volume and we will try to analyze only the control volume within the system. Okay, so that is the one thing. So let us look into some of the assumptions which are made while deriving the SFEE. Okay, okay. In a steady flow system, following assumptions are made. Can anyone read the first statement here? Yes. The first statement. Sagar. Sagar is Acharya.
Yes, sir.
So read out the first assumption.
Just a second. That the pen color panel is blocking the.
Yeah, man. It's gone, I guess. No? So how much would be the delay? Man, if I do something, means I'll be writing an equation. There would be definitely delay, but whether the delay would be too much significant to understand, whether it interrupts you while understanding things because I'll be writing something, uh, whether there will be delay in my voice and whatever I write, too much delay or it is manageable.
Sir, I don't know actually because it's raining here. It's my network or your network. I don't know. So
My network is always fine because I connect to the Wi-Fi and I shift eventually a different place where I can access more amount of Wi-Fi. Okay, so I guess no problem with my network. I want the answers from the others. Whether the delay is too much um, between the voice and what I
Okay,
write.
it's okay. It's okay.
Manageable.
It's okay, right? Okay. Okay. Yes. The first statement. Gautam H.S.
Yes, sir. The state of the
Read
fluid
out the
at
first
each
assumption.
the state of the fluid at each point in the control volume does not vary with time.
The same example which I've just stated, length of a pipe where you consider the control volume over there, the state of that particular point, suppose the state, if you have considered that to be a state 1, the pressure and volume and temperature of that particular state will not change with respect to time. So that is your first assumption. Number second, Rakshanji. Yes, besides that we had a network issue. Okay, Amrut M. Acharya.
Okay.
Yeah, second assumption. Man.
The
So it's a
net
long thing.
amount,
Read out.
the net amount of heat and work entered in the control volume for a
Mm-hmm. Specified.
specified
So I'll be
time.
correcting.
Time.
Many of you are asking me the doubts regarding the notes which I sent. Man. So this is not written by me.
Must be equal to the
Previous
sum of
student. I have just
net
taken the notes
amount of.
from her. Okay.
Okay.
Net amount of heat
Uh,
and work
so,
leaving the control volume for a same interval of time. Yeah. What does
same,
it mean? I'll just try
okay.
to explain it. Okay. Suppose again there is a consider a pipe and control volume in between like this. Okay. So I consider this to be a 1 1. I consider this to be a 2 2. That means plane 1 and plane 2. Okay. Now, from the flow is in this direction in the sense from 1 1 it gets in and from 2 2 it gets out. Okay. What he says is the amount of fluid which gets in and gets out at inlet and outlet should be same. That means whatever the mass would get in, it has to be the same mass has to get out of the system for a particular interval of time. So that is your assumption number 2. Assumption number 3. Shravan Pujari. Shravan? Sriraj?
Yes, sir.
So read out the third assumption.
The mass flow rate at the inlet and outlet of a control volume must be constant.
That is what I've just said. So mass flow rate must be equal. The mass is different and the mass flow rate is different. So I would like to highlight on this. So M indicates mass, whereas M dot indicates mass flow rate. Okay. So what do you mean unit of mass? Unit of mass is just kg, but the mass flow rate is kg per time. So I can take it as kgs per second. Okay. The next assumption, Shashank. Yes. Shashank. I think it is the last one. No, two. Shashank. Sumant.
Yes, sir. The control volume does not move relative to the coordinate frame.
Coordinate frame. So the control volume does not move to the coordinate frame. That is what he means. That means that whatever the control volume you specify on this, like this, suppose if you choose this to be a control volume, and this particular control volume will not move with respect to the coordinates like this. So it will not move. It has to be fixed at a particular point. That is what he says. That is your assumption. Okay. Next one, the last one. Sriraj.
Fluid is uniform in its composition and will not change its chemical composition.
I think there is no explanation required for this particular sentence. So it just says fluid should be uniform throughout its composition, and even the chemical composition of it should not change. So that is your the last and fifth assumption. Now, we have said that we are deriving an equation called as SFEE, which is steady flow energy equation. So what do you mean by a steady state condition, which is given here? When a system exists in the steady state or a particular location, the thermodynamic properties will have the fixed values. That is the steady state condition. So the thermodynamic properties will have the fixed values and will not change with respect to time. So all the thermodynamic properties at a particular location will not change with respect to time. Then you can say the system is in steady state condition. Okay, that is what it is meant. Okay, let us start the derivation of the steady flow energy equation. So steady flow energy equation, you have to first consider a figure like this. Okay, usually I mark this as a steady flow energy device, which could be anything. It could be your pump, it could be your compressor, it could be your turbine, it could be your valve, anything it might be, which is a steady flow device. Okay, just so this is a steady flow device. Okay, for this steady flow device, the flow gets entered in this particular thing here. So here at the section 1.1, the flow gets entered, and in the section 2.2, the flow gets out of the system. Okay, and this the area of cross section of this particular thing is A1, and the area of cross section of the outlet is A2. Okay, and the section plane of the one is situated at the height of Z1, and the section plane of 2 is situated at the datum head of Z2. Okay, so these are all, again, you can even write the same things. This is the mass flow rate at the inlet, and here is the mass flow rate at the outlet. Enthalpy at the inlet, enthalpy at the outlet. Okay, all other parameters you can define. Even the velocity also, the velocity with which it gets in the system, velocity with which it gets in. So like I can take it as C1. Velocity with which it gets out of the system, I can take it as C2. Okay, all those parameters are mentioned here. Okay, you can just look into it. Okay, I'll just read out. Okay, let A1 and A2 be the cross section area of the stream at inlet and outlet respectively, which is measured in meter square. Here it is m1 and m dot 1 and m dot 2. I said you m is just a mass and m dot is mass flow rate. So m dot 1 and m dot 2 be the mass flow rate at inlet and outlet kg per second respectively. Okay. The next one is P1 and P2 be the absolute pressure in Newton per meter square, and small v1 and small v2 be the specific in volume. Just remember, capital V is your volume, okay, and small v is your specific volume. Okay, small v is your specific volume, and small v divided by m will be your specific volume. So when you divide a property with its mass, it becomes a specific property of this particular thing. Okay, wherever is let U1 and U2 be the specific internal energy at inlet and outlet, which is joules per kg because it is a specific thing. Similarly, H1 and H2 be the specific enthalpy, joules per kg. C1 and C2 are the velocities at inlet and outlet, which is in the meters per second. Okay. Z1 and Z2 be the elevations above the reference plane at inlet and outlet, which is in meters. Okay. Now, Q is given by dq by dt. This you know, the rate of flow of fluid is known as heat energy. So Q is nothing but the amount of heat at which it flows is known as net heat rate transferred. Okay, this is W is nothing but the net work rate transferred. So these two are very important. I have said heat and work are always important in thermodynamics. Okay, so Q is your capital Q is your net heat rate, whereas the capital W is your net work rate. Okay, where T is in time in seconds. The principle of conservation of mass states that m1 should be equal to m2. What does it mean actually? Okay, suppose if 10 kg of fluid is getting inside the system, at the outlet also you should expect how much? That same 10 kg of fluid should get out of the system. That means none of the system, no particles of the system are within the system. I mean, no particles of the fluid are within the system. That means whatever it is getting in should get out within the same amount. So that is what it means. So this m1 should be equal to m2. Okay, whatever it is getting in, so it should be equal to the outside. So that is what he says. The mass flow rate at the inlet will be equal to the mass flow rate at the outlet according to what? The principle of conservation of mass. Even you know this. Okay. The principle of conservation of energy states that the rate of flow of energy. Now we are talking about the energy. So until now we have talked about the mass. Now we are talking about the energy. What does it say? It says that whatever the flow of energy, that means the rate of flow of energy which is entering the control volume must be equal to rate of flow of energy leaving the control volume. Okay, the rate of flow of energy which is entering the control volume must be equal to rate of flow of energy leaving the control volume. By this I can write, so this particular expression, this is the rate of flow of energy entering the control volume. This is the rate of flow of energy leaving the control volume. Okay, in this there are three different terms here. The number one is primarily the energy. Okay, m dot 1 into E1 is the primarily the energy. M dot P1 into V1 is your flow work, I mean the flow energy, and Q is your heat energy. So heat is always inputted and the work is extracted usually in any of the thermodynamic systems. So you just provide the heat, the system will give you back the work. So that's why heat is incorporated here and work is incorporated here. And similarly, it goes to the outlet also. So basically, you try to understand there are three different forms of energy. Just I'll specify below this. The number one is nothing but the plane energy itself. Next one is the flow energy. Okay, the last one would be heat or work. The last one would be the heat or work. Okay, now that is what is indicated here, I guess. Yes, E1 and E2 are the energy at inlet and outlet of the control volume. P1, V1 and P2, V2 are the flow work at the inlet and outlet respectively. Now, what is this total energy? I already said you that total energy is given by the kinetic energy plus potential energy plus the internal energy. So three factors constitutes your total energy. So total energy is half mc square, which is the kinetic one, and mgz, which is the potential one, and u being the internal energy. Now dividing the entire thing by m, what happens? What happens when you divide the entire thing by m? So m goes away, it would be just c square by 2 here. Okay, it would be c squared by 2. Here also m goes away, it would be gz. Okay, plus capital U divided by m would be the small u. Clear? Capital U divided by m would be your small u. Okay. Now, substituting this particular thing here, E value in the above equation. So you can take this as equation 1, which is this. Okay. You can just write here equation 1, substituting E value. So m dot 1, this is the E1 value. Okay. Similarly, you can write it here. Similarly, I can write E1 is equals to C1 square divided by 2 plus G into Z1 plus C1. And E2 is equals to C2 square by 2 plus G into Z2 plus C2. Okay, just have manipulated in terms of section 1 and section 2. So I have substituted E1 here and substituted E2 here. Okay, remaining two expressions, which the flow work and the heat, flow work and the work output would remain same there. It is m dot P1 V1 plus Q, m dot P2 V2 plus W. So what I have done is I have just substituted the value of E1 and E2. Okay, once I have done, just what you have to do, you have to multiply the things here. Okay, just multiply the things. If you observe this particular term here, okay, if you observe this particular term, okay, what does it say? What are the contents in it? It is U1 plus P1 V1, and here it is what? U2 plus P2 V2. First of all, what is U plus PV? What is this? What is U plus PV? Yes?
H.
Exactly. So U plus PV is nothing but your enthalpy. Suppose if I take it as the first section 1, it is U1 plus P1 V1, it will become H1 here, and U2 plus P2 V2 will become H2. Okay, simple. So just I will be replacing this particular term with H1, which is this. Okay, and I'll be replacing this particular term with H2. So whatever the expression you get, finally, that is your SFEE. So SFE is a very long expression, very easy to remember, okay, and very important too. So it says M1 dot into C1 square by 2 plus G into Z1 plus H1 plus Q will be equal to M2 dot into C2 square by 2 plus G into Z2 plus H2 plus WF. Okay, so this is your SFEE, steady flow energy equation, which compares the inlet parameters with the outlet parameters. Okay, so that is your SFEE. This equation is known as steady flow energy equation. Streams. Understood? Any doubts in this derivation? It's very simple. Any doubts here? Any doubts, guys? Okay. What about others? Understood?
Yes, sir.
Yes, sir.
Okay, so this is very, very important. It is reviewed many times. Okay. Now, how to apply this SFEE if you have multiple inlets and multiple outlets? Okay. Okay, someone has messaged me. Okay. So many are facing problems when. Okay, fine. So control volume, if it is having a multiple inlets and multiple outlets, as in case, this particular case here, it's M1 dot here, right? It is M1 dot, which is entering, and M2 dot is entering, and M3 dot is exit, and M4 dot is exit. So how to apply SFEE for this? Okay. So same thing. Always remember its inlet plus Kev will be equal to outlet plus WF. Whatever amount of inlet could be, you can just add it up here. Whatever amount of outlet could be, you can just add it up here. As simple as that. So this is your first stream, energy balance for the first stream, which says m dot 1 into h1 plus c1 square by 2 into g into z1 plus m2, which is again entry. So that's why it is in the LHS part of the expression. M dot 2 into h2 plus c2 square by 2 into g into z2 plus kf, this is very important, is equal to the outlets now. M3 into h3 plus c3 square by 2 into g into z3 plus M4 into h4 plus c4 square by 2 plus z4 into z4 into c plus your work done. So work done will come always on the RHS, and the heat flow would come always on the LHS. Okay, you can even use this particular expression, mass flow rate. You know that the mass flow rate is given by area into velocity into density. Here the velocity is taken as C. That's why it is A1 C1 into rho 1, which gives you the mass flow rate. Okay, so M1 plus M2. The inlets should be equal to outlets. Correct. So inlets are M1 and M2. Outlets are M3 and M4. That's why M1 plus M2 should be equal to M3 plus M4. That will be in turn equal to, you can just expand. So you know what is M1, right? M1 dot is equals to A1, C1 and rho 1. So you have to remember this. It is very useful in the problems also. M dot 1 is equals to A1, C1 and rho 1. And M2 is equals to A2, C2 and rho 2. Similarly, M3 is A3, C3 into rho 3. And M4 dot is A4, C4 and rho 4. Okay, these are the applications how we will apply to a system. Now we will be taking the individual components like turbine, pump, and applying the SFEE to it, and we will be calculating the final expression. That means reduced expression. It's not the final expression. You can say it's a reduced expression. Note, guys, you no need to remember the individual formula for individual application. There will be problems given to you in terms of a compressor. There will be problems given to you in pump, turbine, and every sort of devices. And every sort of devices has its own expression. So no need to, remember all the final expressions. Just SFEE, if you remember, that's more than enough. Okay, whatever we are doing it, this for the theoretical basis. Sometimes he could ask, apply SFEE for the pump, apply SFEE for the compressor, apply SFEE for the turbine. Then you have to write the diagram, just a flow diagram like this. Okay, a description and application. How do you have applied your SFEE? You have to write it. So that will fetch you the full marks. These three components should have. The number one is the diagram. Number two is little sort of description. Number three is application of SFEE. So if you just write SFEE, out of 6 marks, you'll get 2 marks straight away. Okay. So that is how it goes. Let's see. Okay, compressor. The first expression is for the compressor. So these are all the work absorbing devices. That means here in these devices will be working on the system. So you cannot expect the work from the system. So compressor in the sense will be working on the system, is it? So that's why. So first we shall list out all the work absorbing devices. Okay, the compressor can be considered as a turbine operating in reverse forth. That's why for the turbine it is as such. Inlet is here and outlet is here, where expansion occurs. But in the compressor, it's the reverse fashion where compression occurs. Okay, so the compressors can be considered as a turbine operating in reverse fashion, and its fashion. Okay, I'll correct it now itself. This is ION. Okay, reverse fashion. It is a work absorbing device which increases the pressure of the fluid by working on it. Okay, simple description. No need to write the theories of compressors. That's not required. So the air gets entered here. So this I will be marking it as 1, 1. And air gets outlet here. Okay, which I'll be marking it as the 2, 2. Okay, the shaft work power output you are giving, that's why it is W1 to 2, okay, which is negative. Okay, and Q1 to 2 is here, the heat exited from the system. Okay, nav. Yes, anything else? Nothing. So this is very important. For every engineering application, there would be suitable things you can eliminate. So what is eliminated for what substance, for what equipment is very, very important to be understood and to be by hearted. Okay. In the compressor, what happens usually, you will neglect the kinetic energy and the potential energy. Remember, for all the systems, irrespective of anything, you will be neglecting the kinetic energy and the potential energies because it is a thermodynamic study. Okay. Next, the work done on the system, that's why work done would be what? It would be negative. So work done, it is on the system, that's why work done would be negative. That's great. The system rejects the heat. That's why it is negative again, because heat is rejected from the system. You're not adding heat to a system. So generally what happens, if heat gets rejected from the system, it would be negative. So I say the heat, it would be an adiabatic device. Adiabatic device in the sense, I told you Q value should be 0. Name the process in which the value of Q is 0, that is your adiabatic process. Name the process where the value of work done, W is 0, that is your, which one?
Isocoric.
That's great. So the isochoric process is the process in which work done is 0. Adiabatic process is the process in which the heat flow is 0. So we will be considering this particular compressor to be an adiabatic. So what happens is there is kinetic and potential energies are just 0, taking them to 0 on the both sides, that is inlet and outlet in. Okay. Now the heat flow would be 0 because we have assumed it to be an adiabatic system. That's why the heat flow would be 0. What would remain is m dot into h2 minus h1, and the work done would be given as m dot into h2 minus h1. Exactly reverse of this is your turbine. So any doubts in the compressor? Okay, so we are neglecting the kinetic and potential energies. We are treating it as an adiabatic system. That's why Q becomes 0. The only thing remains is this particular thing. Okay, any doubts here? Shall we move on to the next?
Yes, sir.
Yes, sir.
Okay. Next is your centrifugal pump. Centrifugal pump. So in the centrifugal pump, what happens? There would be a water level, okay, from which you will lift up, and water is being sucked in the suction pipe, and it being compressed, and it will be reached to the higher level. So this is the delivery head. I can just write it as Z2. Okay, I can just place my reference plane just to the axis of the axis of the pump. I can just place my reference plane over there, and this is my control volume. Again, I'll be marking. So this is my control volume where I'm actually concentrating at. Okay, and this becomes your Z1 from the reference plane. Okay, and Z2. Okay, see the description. It would be given in a very easiest fashion. Okay, just follow the descriptions here. Now, the pump is used to deliver liquid at higher heads to convert mechanical energy into potential energy. So basically what you are doing, you are giving the shaft input to the system, which converts the shaft energy which is available to a potential energy which is required for the greater heights. Okay. While using SFE in the pump, the following assumptions are made. The work is done on the system, that's why it is negative again. So work is done on the system, that's why it is negative again. Heat transfer is generally zero. There will be no heat transfer in case of a pump, I guess, because it is using a water. So I can take heat transfer to be the value of zero. As water remains the same, the change in the internal energy can also be neglected. So this is very, very important. Because there is no change in the temperature, then the internal energy will be also zero. So the application of this particular thing, that is problems. Okay. So as of now, just remember, since there is a no only dependent on temperature, no temperature change, no internal energy change. That's why even the internal energy change is also zero for the plant. Okay. Now, when you are applying it, so what it goes, okay, because you should not neglect the kinetic energies and potential energies over here. So you should not neglect it. So what happens to it? So you can just write here. So which is U1 plus P1 V1, just an expansion, just going back one step previous in your SFEE derivations. Okay, SFEE derivation, what you have done, you have replaced U1 P1 V1, U1 plus P1 V1 as H1. Now what are you doing? You are just replacing H1 with U1 plus P1 V1. Okay, so just remember in this particular expression, just expand it and write the things. Take this as negative, and this to be zero, because what is the value of Q? Q is zero for an pump. Okay, whatever is remaining, okay, that means keep the value of W on the one side, whatever is remaining, just transfer to the other side and write the expression. Clear? No need to remember it. No need to remember it. Whatever might be the expression, that is correct. So what are you doing is you are not, deriving the expressions, but you are applying the SFE for the different thing. So for application of SFEE for the pump, what are the two things that you have to note down as? The Q value would be zero because there is no heat exchange. As Q value is zero, delta U value would be zero. There will be no change in the internal energy. Work done would be negative. That's it. Okay. Keep the work done on LHS, transfer all the remaining to the RHS. That becomes your expression. That becomes your application of SFEE for the pump. Okay. Now, we shall move to the work developing devices. It would be very much similar, gas turbine would be very much similar with in case of the gas compressor. Okay, same thing would be there. Okay, turbine is a device which is working on the fluid stream or a gas expands from a higher pressure to a lower pressure to develop a power. So what happens in a turbine? You supply a fluid at a higher pressure, there would be a turbine inside it. So this impinging action of your high pressure fluid, what happens? Your shaft power, that means your turbine power would generate because it has performed some work rotating the shaft. This high pressure would be lost, so the pressure would decline at the outlet. Okay, so this is how it is for the turbine. A simple basic description, if you write, that's more than enough. What is important again? This thing is important. The assumptions are made. What are the assumptions are made? The kinetic energy and potential energy are neglected. Same in case of a compressor again. work done by the system is positive because it's a turbine, you are getting work output from the system, that's why it is positive. The expansion of the fluid in the turbine is assumed to be adiabatic. So if you assume it as an adiabatic process, then generally the Q would turn 0. Okay, if you assume the process to be adiabatic, what happens to the Q? Q value would be 0. Applying the same thing again. So steady flow energy equation states that you have to write the steady flow energy equation. Potential and kinetic energies at inlet and outlet are neglected. Okay, Q is neglected. Q is made 0. Why? Because we have assumed it to be an adiabatic process. What is remaining is just the value of H and M. So just put W here and transfer H to the either side. You'll get M into H1 minus H2. If you remember, the work done expression for the compressor was M dot into H2 minus H1. So for the turbine, it is H1 minus H2. Just a small difference over there. Okay, a nozzle. Okay, so other devices. These are you cannot term it as a work observing or a work emitting devices. Okay, these are just flow devices. For such flow devices, how do you apply the SFEE is my question. So it is just a nozzle. It has a diminished cross section by which the pressure and the velocities of that particular cross section would be varied. So that is the function of your nozzle. Is that in order to vary your velocity, in order to vary your the pressure, the nozzles are used with the different engineering applications. So in such applications, whether there would be any work transfer, definitely not, because you are not doing any sort of work in the system. You are just decreasing and increasing the pressures of it. So that's why you can take the work done to be 0. The work done to be 0. Change in the potential energy is neglected. Remember this, because why is it is neglected? The inlet would be of the same height, even the outlet of would be of the same height. So Z1 and Z2, that means the elevations of the inlet as well as the outlet would be same. That's why the change in the potential energy is neglected, but kinetic energy is taken into consideration because that is the main thing which gets affected because of the nozzle. Okay, enthalpy decreases and the kinetic energy increases. This particular thing will be better thought in the problems. You'll understand there. Okay, now what happens to it? What happens to it is usually the mass flow rate at the inlet and the mass flow rate at the outlet. That means the rate of mass flow would be same. That's why H goes away. I mean M goes away. M is inlet and the outlet is same. That's why M cancels here, and the work transfer is 0. Heat transfer is 0. Whatever is remaining is enthalpy plus your velocity. So you can just write C2 square minus C1 square is equals to 2 times of H1 minus H2. It's H1 minus H2. Okay. So just remember what you have to remember in case of a nozzle. In the nozzle, the Q value is 0. The work done value is 0. And your mass flow rate at the inlet would be equal to the mass flow rate at the outlet, and the potential energy at the inlet is equal to the potential energy at the outlet. That's why mgz1 would be equal to mgz2. So your z1 would be equal to z2. By this you can cancel the terms, you can neglect the potential energy. So these are the few concepts that you have to remember to solve the problems of the nozzle. So just if you remember this, what I have written here, it's more than enough. Okay. And next is your boiler. Oh, boiler diagram is not there. So you can just write like, okay, just draw it now. Okay, there will be a boiler like this. Okay, I think it's already time. Okay, we shall do it in the next class, no issue. Steam out. So here it's water in, and here it's steam out. So we'll discuss about the boiler in the next class. So how many thermodynamic applications throttling process is there? Yes, that's it. So only 2 are there left over. We'll discuss in the next class. Okay. No issue. So any doubts till now? Any doubts?
No, sir.
No, sir.
No, sir.
So it's all the theory which I've just explained for the past half an hour was just the application of SFEE. How would you apply the SFEE for the various engineering systems? So certain terms get cancelled. Okay, certain terms has the prominence of it. So which terms get cancelled? Which one is neglected? You have to remember. So that is the final outcome of all the theory which I've just said. Okay. Abdul Rahman. Abhinav.
Yes, sir.
Next is Adarsh.
Present, sir.
Ashami. Mohammad Reza. And those who answer the attendance, they can just leave for the lunch, man, because simply waiting is of no use. Okay. Those who have just answered, they can leave for the lunch. No issue. Mohammad Reza. Akash. Sorry, Akshay.
Present, sir. Actually, present, sir.
Okay. So don't just message me now and leave. Just whoever name is at the last, just wait for a few minutes, man. I'll cover it up fast. When I call your name, you message me. That's okay. Amit Eslahari.
Present, sir.
Next is Amrit.
Present, sir.
Anvat.
Yes, sir.
Ashwin.
Present, sir.
Ashwita.
Present, sir.
Okay. Chandan. Benoy.
Present, sir.
Fahad. Faizan. Gaurav.
Present, sir.
Gautam.
Yes, sir.
Javel.
Present, sir.
M. Karthik. Fazil.
Present, sir.
Fazil.
Present, sir.
Yeah, okay. Muhammad Sihab.
Present, sir.
Next is Tausif Ali.
Present, sir.
Muwaz. Muwaz. Yan Suraj.
Present, sir.
Namita. Nandish. Nartan. Next is Niharika.
Present, sir.
Nishchit.
Present, sir.
Nitin George.
Present, sir.
Omkar Mahesh Patel. Prarthan Jain.
Present, sir.
Pratish Suvarna. Prajat.
Present, sir.
Rakshan K.
Present, sir.
Ramdas.
Present, sir.
Ranjit. Shabit.
Present, sir.
Sagar Sacharya.
Present, sir.
Shahzad Abdullah.
Present, sir.
Shetty Sujay. Okay. Next,
Shashank.
Shashank, why did you not reply when I called you, man?
Sir, I didn't hear.
How come you didn't hear me?
Sir, network issue, sir. I heard Shehzad and Suga, that's it.
Shashank. Shetty Tejas.
Present, sir.
Okay. Shravan Kumar.
Present, sir.
Okay. You also, man, you did not respond, Shravan, when I called you. Sriraj.
Present, sir.
Next is Saurabha.
Present, sir.
Sumant.
Present, sir.
Next is Varun. Vigneshwara. So in the next class, we will come from the reverse, from the bottom to top. Okay. Amit Sangolli.
Yes, sir.
Nilesh.
Present, sir.
Next is Prajwal.
Yes, sir.
Sandesh. Rachan. Rohan. Varun Gopalakrishna. Rachan is there. Okay.
Yes, sir.
Okay. Rohan or Rachan ada?
Yes, sir.
Rachan.
Rohan.
Okay, fine. Varun. Adarsh.
Yes, sir.
Muhammad Amin.
Yes, sir. Present.
Numan.
Present, sir.
Okay, fine. Take care.